In this video, I'll explain my graphics code for plotting the stream function. Let's have a look. I wrote the graphics code as a function with one input argument psi. Psi is the stream function on the psi theta grid. The code is written for a Reynolds number of 10. If you want to plot a different Reynolds number, you might have to slightly modify the code. The first lines of the code set up the psi theta grid. The dimensions of the grid can be grabbed from the matrix psi, and I do that here. Little n is the number of grid points in the psi direction, and little m is the number of grid points in the theta direction. These next variables are the same as the CFD code. The new function here is mesh grid that takes the values of psi and theta and maps them onto a two-dimensional grid. The variables capital psi and capital theta become m by n matrices. The values of little psi are placed in all the rows of capital psi, and the values of little theta are placed in all the columns of capital theta. If you find this confusing, join the club. We'll use capital psi and capital theta for our interpolation. We need an xy grid in Cartesian coordinates to make our plot. I specify the number of pixels I want in the x direction and the number of pixels I want in the y direction. I divide the number of pixels in y by 2 because we'll only need the values in the positive y half of the plane. I also specify the minimum and maximum values of x. Remember, the cylinder has a radius of 1 centered at the origin. So negative 1 is on the cylinder's surface, and negative 1.5 means 1/2 of the cylinder radius in front of the cylinder. 2.5 means 1.5 cylinder radii behind the cylinder. The maximum and minimum values of y are determined by the number of pixels. I then use the linspace function to define the x and y grid points, and the mesh grid function to define the Cartesian grid. We want to interpolate to our Cartesian grid, but our data is on the psi theta grid, so we need to know the values of the Cartesian grid points in the psi theta space. Here, we map the Cartesian coordinates to the psi theta coordinates. We make use of the MATLAB functions log, atan2, and wrap to 2pi. You can look up these functions on the help pages. Log is just the natural logarithm. Atan2 is the arctangent done in a way where you don't need to worry about the sign of x or y. And wrap to 2pi always forces theta to be in the range between 0 and 2pi. If you don't wrap to 2pi, you'll run into trouble with the interpolation because theta is a periodic coordinate. We are now ready to interpolate using interp2, a two-dimensional interpolating function. Here, I just use the default interpolation method, which is linear interpolation. Psi is our values of the stream function on the psi theta grid, and to interpolate properly, we need to take the transpose. This is related to how mesh grid works. Capital psi and capital theta is the CFD grid, and psi sub I and theta sub I is the grid we are interpolating to. So the output of this function, psi sub xy, are the values of psi on the Cartesian grid. When psi sub I is less than 0, our Cartesian grid points are inside the cylinder. So here I use logical indexing to set the interpolated values of psi inside the cylinder to be exactly 0. This will help later with our contour plots. Now we need to set the contour levels and define the color map. I needed to experiment quite a bit to get a pretty plot. I decided to scale the negative values of psi to lie between -1 and 0, and the positive values of psi to lie between 0 and 1. I do that scaling in these 4 lines of code, making use of logical indexing. I then set the contour levels to be evenly spaced between -1 and 1 and define the color map. You can find my choice of jet on the MATLAB help pages. The MATLAB function flipUD just flips the color scheme between positive and negative. The call to color map sets the map. Now we plot the color contours. I use the image_sc function. X and Y are our one-dimensional grid points, and psi sub xy are the values of psi on the grid. I also want to plot color contours for negative values of y, and I can do that by changing the sign of y and the sign of psi. On top of the color contours, I want to plot contour lines to make the plot look even nicer. Here, I specify the lines that I want to plot. Remember that the values of psi go from -1 to 1, so I try to distribute the lines to look as nice as possible. Then we plot the contour lines for positive values of y, and then we plot the contour lines for negative values of y. It looks nice to draw a black circle for the cylinder, and that's an easy thing to do using linspace, the cosine and sine functions, and the fill function. Finally, I neaten up the plot. One of the things we need to do is make sure the y direction is specified as normal. Otherwise, it's upside down. We also set the axis limits, set the background color to white, and turn the axis off. And I want to display the value of the Reynolds number on the plot, so I do that here. I hope this has given you some insight into how I wrote the graphics code. After you pass the grader, feel free to modify the code to suit your purposes. If you increase the Reynolds number, you'll need to increase the domain behind the cylinder to capture the entire separation vortex. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.